Class 11th chemistry, we were discussing unit 7 equilibrium, and in this video we will discuss about solubility product constant. First of all, we discuss the classification of salts on the basis of their solubility. On the basis of solubility, salts can be classified into three categories. Category 1, these are soluble salts. For them, solubility is greater than 0.1 m. Category 2, slightly soluble salts. Solubility is less than 0.1 m but more than 0.01 m. Category 3rd, sparingly soluble salts. Solubility is less than 0.01 m. For a salt to dissolve in a solvent, the strong forces of attraction between its ions must be overcome by the ion solvent interactions. Okay, and this force of attraction can be expressed in terms of lattice enthalpy. That is magnitude of force of attraction between ions expressed in lattice enthalpy. This is the enthalpy change when 1 mole of solid ionic compound is completely dissociated into its constituent gaseous ions. Okay. The solvation enthalpy is always negative. Now, what is the solvation enthalpy? When gaseous ions are solvated, okay, then whatever the change in enthalpy, that is solvation enthalpy, and it is always negative. It means energy is released in the process of solvation. And if solvent is water, then we use this hydration enthalpy, and that process is known as hydration. Okay. For a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy. Okay, and if we consider the solution or dissolution of any salt in a water, then we compare the hydration enthalpy and lattice enthalpy. If hydration enthalpy is greater than lattice enthalpy, then that salt is dissolved in the water. And if lattice enthalpy is greater, then it will not dissolve in the water. Solubility product constant. Consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution, BaSO4. And this is saturated solution in water. Then there is equilibrium between solid BaSO4 and its ions Ba2 plus and SO4 2 minus. And for this equilibrium, we can write the equilibrium constant expression K is equal to concentration of Ba2 plus multiplied by concentration of SO4 2 minus divided by concentration of BaSO4. But for a pure solid substance, the concentration remains constant, so this can be written like this. In this case, this BaSO4 is in solid state. So this K is a constant and BaSO4 is also constant, so we will get the new constant, and that is represented as Ksp, which is equal to product of the concentration of Ba2 plus and SO4 2 minus, where Ksp is the solubility product constant or simply solubility product. Then how can we define this solubility product constant? For a solid in equilibrium with its saturated solution at a given temperature, the product of the concentrations of its ions is equal to its solubility product constant. Clear? The concentrations of the ions will be equal to the molar solubility of salt. If molar solubility is S, then Ksp is equal to concentration of Ba2 plus multiplied by concentration of SO4 2 minus, and if solubility is S, then if S moles of BaSO4 is soluble, then we will get the S mole of Ba2 plus ion and S mole of SO4 2 minus. So in the solution, concentration of a Ba2 plus is S and concentration of SO4 2 minus is also S. So S multiplied by S, we will get S square. That is Ksp is equal to S square. For barium sulfate at 298 Kelvin, Ksp is 1.1 into 10 to the power minus 10. And with the help of this Ksp, that is solubility product constant, we can find out the solubility of this salt by using this Ksp. This is equal to S square. So we can say this S is equal to square root of Ksp. Okay, so if we take the square root of this 1.1 into 10 to the power minus 10, you will get 1.05 into 10 to the power minus 5. Thus, molar solubility of barium sulfate will be equal to 1.05 into 10 to the power minus 5 mole per liter. A salt may give on dissociation two or more than two anions and cations carrying different charges. For example, zirconium phosphate. It's formed like this: Zr3PO4 whole 4. Okay, how can we write this formula? Actually, in this case, this zirconium, it has 4 positive charges and its valence is 4. Phosphate, this is PO4 having charge 3 minus and its valence is 3. Okay, and how can we write the formula? This 3 will go to this side and 4 will go to this side. So we will get Zr3PO4 whole 4, zirconium phosphate. It dissociates into 3 zirconium cations of charge plus 4. That is, each zirconium cation having charge plus 4, and 4 phosphate anions, and each phosphate anion has charge minus 3. And this can be represented like this. This is zirconium phosphate in solid state, and when it dissolves, it gives the ions 3 ions of zirconium 4 plus and 4 ions of phosphate 3 minus. If the molar solubility of zirconium phosphate is S, then we can say concentration of zirconium 4 plus ion is 3S, and concentration of phosphate ion is 4S. So we can write KSP is equal to concentration of zirconium ion power 3, concentration of phosphate ion power 4, and concentration of zirconium ion is 3S. So KSP is equal to 3S power cube, and concentration of phosphate ion is 4S. So 4S power 4. And if we solve it, we will get 6912 S power 7. Okay, so we can write S power 7 is equal to KSP divided by 6912. So S, that is solubility of zirconium phosphate, this is equal to KSP divided by 6912, and it's 1 by 7. Its power 1 by 7. Okay, if we know the KSP of zirconium phosphate, we can find out solubility of zirconium phosphate. Now consider the one question, problem 7.26. Calculate the solubility of A2X3 in pure water, assuming that neither kind of ion reacts with water. The solubility product of A2X3, that is KSP, is given 1.1 into 10 to the power minus 23. This is the equilibrium between solid A2X3 and its ions. A2X3 gives 2A3 plus 3X2 minus. Okay, we can write KSP is equal to concentration of A3 plus power 2, concentration of X2 minus power 3, and this is given 1.1 into 10 to the power minus 23. If S is the solubility of A2X3, then concentration of A3 plus is equal to 2S, concentration of X2 minus is equal to 3S. Therefore, KSP is equal to 2S power 2, 3S power 3, and if we solve it, we will get 108 S power 5, which is equal to 1.1 into 10 to the power minus 23. So we can find out S. First, S power 5. This is equal to 1.1 into 10 to the power minus 23 divided by 108, and if we solve it, we will get 1.1 into 10 to the power minus 25. So S is equal to 1.0 into 10 to the power minus 5 mole per liter. Okay. Now one more question, problem 7.27. The values of KSP of two separately soluble salts, NiOH twice, nickel hydroxide, and AgCN, silver cyanide, are 2.0 into 10 to the power minus 15 and 6 into 10 to the power minus 17 respectively. Which salt is more soluble? Okay, to find out this, we have to calculate the solubility of each salt. So first of all, for AgCN, this AgCN is equilibrium with Ag plus ion and Cn minus ion. Okay, and for this we can write KSP is equal to concentration of silver ion multiplied by concentration of cyanide, and that Ksp is given 6 into 10 to the power minus 17. If solubility of AgCN is S1, then concentration of Ag plus and concentration of Cn minus both are equal and equal to S1. So S1 square is equal to 6 into 10 to the power minus 17. So S1 is equal to square root of 6 into 10 to the power minus 17, and this is equal to 7.7 into 10 to the power minus 9. In the same way, we can find out the solubility of nickel hydroxide. Consider the equilibrium in nickel hydroxide. NiOH twice give Ni2 plus and 2 OH minus ion. Ksp for this, concentration of Ni2 plus multiplied by concentration of OH minus its square, and this is equal to 2.0 into 10 to the power minus 15. If solubility of NiOH twice is S2, then concentration of nickel ion is S2 and concentration of hydroxide ion is 2S2. So S2 multiplied by 2S2 square, and this is equal to 2.0 into 10 to the power minus 15. And if we solve it, we can find out S2 is equal to 0.58 into 10 to the power minus 4. Now just compare this one and this one. Which is greater? Definitely this is greater. So we can say NiOH twice is more soluble than AgCN. Okay. Thank you. Subscribe my channel to get the next video from new chapter redox reaction.